Section 1.3 Evaluating Limits Analytically. In this lesson, you will be able to evaluate a limit using properties of limits. Second, develop and use a strategy to find limits. Third, evaluate a limit using the dividing out technique. Fourth, evaluate a limit using the rationalizing technique. And lastly, evaluate a limit using the squeeze theorem. First, let's talk about the properties of limits. In the previous section, we have seen that the limit of the function as x approaches c does not depend on the value of the function at x equals c. But sometimes the limit of the function is precisely equal to f of c. Such is the case when the function given is continuous at c. So in that aspect, we can just evaluate the function using direct substitution when we try to evaluate the limit of the function as x approaches c. So that is, when you evaluate the limit of the function f of x as x approaches c, and this function f here is continuous at c, the limit as x approaches c of the function f of x is just the value of the function evaluated at c. So you can just use direct substitution for this. The only consideration is that the function must be continuous at c. Otherwise, you cannot use this direct substitution method. So to take note of that, we have the following theorem here. Let b and c be real numbers and n is a positive integer. If you get the limit of a constant, b is a constant, as x approaches c, so notice that b is not dependent on x, this is just a constant. So therefore the limit of the constant is just equal to the constant. So the limit of b as x approaches c is just equal to b. And the limit of x as x approaches c is equal to c. You can just replace x here by c, because this is just saying that the function f of x is equal to c, or to x. F of x in this case is just equal to x, so we just have a line at that point, the line f of x equal to x, which is a diagonal line, and that is continuous everywhere. So it is also continuous at c. So the limit of x as x approaches c is just equal to c. And similarly, if you have x to the n, this is also continuous everywhere. So the limit of x to the n as x approaches c is just equal to c to the n. Just use direct substitution, replace x here by c. And so the limit of x to the n as x approaches c is equal to c to the n. For example, the limit of 3 as x approaches 2 is just equal to 3, because the limit of a constant as x approaches to whatever number is still equal to that constant. That was in the theorem 1.1. Next, the limit of x as x approaches negative 4. Here, x is continuous everywhere, so we'll just use direct substitution. So replacing x by negative 4, therefore the limit of x as x approaches negative 4 is just equal to negative 4. Next, let's evaluate the limit of x squared as x approaches 2. Using direct substitution, since x squared is continuous everywhere, so therefore that is also continuous at 2. So the limit of x squared as x approaches 2 is just equal to 2 to the 2, which is equal to 4. In this theorem here, we will discuss the properties of limits that would be very useful to you when evaluating limits. Suppose we have real numbers b and c, and n is a positive integer, and f and g are functions with limit of f of x as x approaches c is equal to L, and the limit of the function g of x as x approaches c is equal to k. So first, for the scalar multiple, if we want to evaluate the limit of the function f of x times b as x approaches c, you can just take out this constant here outside of the limit, and so therefore you have b times the limit of f of x as x approaches c, and then we know that the limit of f of x as x approaches c is just equal to L. So therefore the limit of b times f of x as x approaches c is just equal to b times L. Second, for the sum or difference rule, if we try to evaluate the limit of f of x plus or minus g of x as x approaches c, and given that the limit of f of x as x approaches c is L, and the limit of g of x as x approaches c is k, then next property is just saying that we can distribute this limit here to the functions here. So this is just equal to the limit of the sum and difference is just equal to the difference or sum and difference of the limit. So this is just equal to limit of f of x as x approaches c plus or minus the limit of g of x as x approaches c. And so therefore we have L plus or minus k here, because L is the limit of f of x as x approaches c, and k is the limit of g of x as x approaches c. And that is also the same for product. The limit of the product of the two functions f of x, g of x as x approaches c is just equal to the product of the limits. This L and k here are the products of, the L and k here are the limits of the functions f and g as x approaches c respectively. Similarly, for quotient rule, the limit of the quotient is equal to the quotient of the limit. L is just the limit of the function f of x, this function, as x approaches c. And k is the limit of this function g of x as x approaches c. So again, the limit of the quotient is equal to the quotient of the limit. And for the power rule, when you evaluate the limit here, it's the same as taking this limit inside this or into the base. And so we have, this is the same as the limit of f of x as x approaches c, parenthesis raised to n. So that's how you get L to the n. Let's consider the example here. Let's evaluate the limit of 4x squared plus 3 as x approaches 2. We will use the properties of limits to evaluate the limit here. First, let's rewrite the limit of 4x squared plus 3 as x approaches 2 as the limit of 4x squared as x approaches 2 plus the limit of 3 as x approaches 2. In a way, we just distributed this operator here over addition, so inside the parentheses. So this is just equal to this. So this is using property number 2 of theorem 1.2. Then next, this one, if we evaluate this limit here, this is a constant times a function. What we can do is we can just take out the constant outside of that limit. So that's why you have 4 times the limit of x squared as x approaches 2. And then we have here the limit of 3 as x approaches 2. Just copy the limit of the constant. And then we can now evaluate the limit. For this one, we can use direct substitution. We can replace x here by 2. So therefore, we have 4 times 2 squared. So this is just 2 squared. Replace x here by 2. And the limit of the constant is just equal to that constant. So that is just equal to 3. Now, 2 squared is equal to 4. So therefore, we have 4 times 4 plus 3, and that is equal to 19. Our result can be verified by looking at the graph of the function f of x equal to 4x squared plus 3. So this is the graph of that parabola. And if we evaluate the function f of x equal to 4x squared plus 3 at x equals 2, we get 19. And this is actually that point here. So if you look at the graph here, graphically speaking, if you look at the values at the left side of 2 and see where the graph would approach to, we would see that as x approaches 2 from the left, f of x approaches 19. And as x approaches 2 from the right, the graph would actually approach also to this point here. So f of x approaches 19. Generally speaking, the direct substitution method is valid for any polynomial function. Like in the previous example, we could think of this function here as a polynomial function. And when we evaluated the limit of a polynomial or of this polynomial function as x approaches 2, we found out that this is just equal to p of 2, which is just the value of the function evaluated at x equals 2. So this direct substitution will work for any polynomial function, and sometimes also for any rational function. This will work for rational functions with non-zero denominators. That means that if you evaluate a rational function and the denominator is not 0, then the direct substitution will work. Otherwise, we have a different discussion on that one. So to formalize this, we have this theorem 1.3 here. If you have p, which is a polynomial function, and c is a real number, then the limit of the polynomial function p of x as x approaches c is just equal to p of c. And if r is a rational function given by p of x over q of x, so if r of x is equal to p of x over q of x, and c is a real number such that q of c is not 0, so if you evaluate this q here at x equals c, you get a non-zero value, then this property here will hold. So then the limit of the rational function r of x as x approaches c is just equal to the value of the rational function evaluated at c. That is p of c over q of c. For example, let's evaluate the limit of this rational function here at x approaches 1. So the limit as x approaches 1 of a rational function when the denominator is evaluated at this value here is not 0 is just equal to the value of the rational function evaluated at this point. So to do that, we will have to evaluate first our function, or this function, this expression at x equals 1. So x here will be replaced by 1, so you have 1 squared, and then here by 1, so you have 1, and then just copy 2. The denominator will just be 1 plus 1. And then you have 1 squared plus 1 plus 2 divided by 1 plus 1. Then simplify this. The numerator 1 squared is equal to 1 plus 1 is 2 plus 2 is 4. And then 1 plus 1 is 2. So you have 4 over 2, which is equal to 2. Now, we can verify our result graphically. So if you graph this function, or the graph of this function is this curve here, And then we see that that function is actually continuous at x equals 1. And then if you look at if you go check graphically the limit of the function as x approaches 1, either from the left or from the right, you'd see that the values approaches this one. So the y values approaches 2. So the graph actually approaches to this point here, and that corresponds to f of x equals 2 or y equals 2. The polynomial functions and the algebraic functions are two of the three basic types of algebraic functions. Now, in this next theorem here, we will discuss how we will deal with the limit of the third type of algebraic function, the one that involves a radical. So in here, if we have n to be a positive integer, if this n here is a positive integer, of course, greater than 1. And the limit of the nth root of x as x approaches c is just equal to the nth root of c, where c here should be greater than 0. So this c here must be positive, and n here must be a positive integer greater than 1. In that case, the limit of the nth root of x as x approaches c is just equal to the nth root of c. So therefore, direct substitution would also hold for algebra or for rational or radical functions. This next theorem here will greatly expand your ability to evaluate limits. This shows you how to analyze the limit of a composite function. Now suppose we have functions f and g, both are continuous, and the limit of g of x as x approaches c is L, and also the limit of f of x as x approaches L is f of L. Then the limit of the composite function or the composition of f and g is just equal to f of the limit of g of x as x approaches c, and that is just equal to f of L. In other words, when you get the limit of the composition of two functions, what you can do is just evaluate the limit first of the innermost function, and then whatever you get from there, you evaluate the function at that point. You evaluate the outer function at that value of the limit. As an example, let's consider these two items here. Let us evaluate the limit of the square root of x squared plus 4 as x approaches 0. Now, before we proceed, we know that we can just use direct substitution here, because this is one of the basic function. So when you just use direct substitution, we can have 0 squared plus 4, that is just equal to 4. So the one inside the radical sign or the radicand is just equal, the limit is just equal to 4. And then the square root of 4 is equal to 2. So that is the value you get by just using direct substitution. Now, let's try to analyze this or solve this on an alternative way by using the limit of a composite function. Now, if we use the limit of a composite function, we would think first of a function. So we'll divide this into two functions. We can have a function that is equal to x squared plus 4. And then take the limit of that one as x approaches 0. So you have the limit of x squared plus 4 is just equal to 0 squared plus 4. And that is just equal to 4. And then next, let's think of a function where would we compose this function to get this. And that is the function square root of x. Notice that the composition of this function and this is just equal to this expression here. So if this is my f of x and this is my g of x, so this one will just be f of g of x. And now, if we evaluate the limit of the square root of x as x approaches 4, that is equal to square root of 4, and square root of 4 is 2. And that's the same as what we got by just using direct substitution. And so therefore, we can conclude that the limit of the square root of x squared plus 4 as x approaches 0 is just equal to the square root of 4, which is equal to 2. And so for letter B, we will first obtain the limit of 2x squared minus 10 as x approaches 3. Using direct substitution, this is just equal to 2 times 3 squared minus 10. And 3 squared minus 10, 3 squared is actually 9, times 2 is 18, minus 10, that gives you 8. And then the other function where we would compose this to get the original function is the cube root of x. Now let's evaluate the limit of cube root of x as x approaches 8. So cube root of 8 is just equal to 2. So therefore, we can conclude that the limit of the cube root of 2x squared minus 10 as x approaches 3 is equal to the cube root of 8, which is equal to 2. And you can also verify that you can just use the direct substitution method here and get the limit. Now you have already seen that the limits of many algebraic functions can be evaluated by direct substitution. The 6 basic trigonometric functions can also be evaluated using direct substitution. So in this theorem here, we see that the limit of sine of x as x approaches c is just equal to sine of c. And the limit of cotangent of x as x approaches c is just equal to cotangent of c. Similarly, the limit of cosine of x as x approaches c is equal to cosine of c. And the limit of secant of x as x approaches c is equal to secant of c. And also, the limit of tangent of x as x approaches c is tangent of c. And the limit of cosecant of x as x approaches c is equal to cosecant of c. So all of the 6 basic trigonometric functions exhibits the quality that the limits of these functions can also be just obtained by using direct substitution method. So therefore, if we are going to evaluate the limit of tangent of x as x approaches 0, that is equal to tangent of 0, and tangent of 0 is just equal to 0. Second, find the limit of the product of x times cosine of x. So we know that the limit of the product is also equal to the product of the limits. So we can first evaluate the limit of x as x approaches pi, and then multiply that to the limit of cosine x as x approaches pi. Now here we can use direct substitution. We can just replace x here by pi, so you have pi. And then here, the limit of cosine x as x approaches pi using direct substitution is just equal to cosine of pi. And cosine of pi is just equal to -1. So therefore, you have pi times -1, which is equal to -pi. Letter C, limit of sine squared times limit of sine squared of x. So this is the same as, so this is actually of the form, or this is like an exponential function. So to evaluate the limit of this, we can just evaluate the base first, which is sine x. So we have the limit of sine of x as x approaches 0. So the limit of sine of x as x approaches 0 is equal to 0. So you have here 0, and then you square it because this is being raised to 2. So 0 squared is still equal to 0. Now let's discuss strategies for finding limits other than direct substitution. Now you already have seen several types of functions whose limits can be evaluated by using direct substitution. This knowledge, together with the next theorem here, can be used to develop a strategy for finding limits. Now let us consider functions that are equal at all except possibly at one point. Suppose we have f of x and g of x, the two functions that are equal for all x except possibly at x equals c. And this c here must be a real number. Now, if the limit of this function g of x as x approaches c exists, then therefore, the limit of this function as x approaches c also exists, and that is just equal to the limit of g of x as x approaches c. Now that theorem can now help us evaluate limit of functions that are like this. This function here, if I'm going to evaluate this function at x equals 1, so if I'm going to use direct substitution method, I would actually get a 0 in the denominator. So as previously discussed, the direct substitution method would not work in that case. So now what we're going to do here is first, let us get this expression here. Let f of x be equal to this expression here. And then we will simplify. We will simplify this by factoring first the numerator. This numerator can be factored into x minus 1 times x squared plus x plus 1. And then copy the denominator. Notice that I can cancel out this common factor here. You can cancel x minus 1 in both in the numerator and in the denominator. And so therefore, we have another function which is equal to x squared plus x plus 1. Notice that this x squared plus x plus 1, if you check, this has the same graph as this function here, except at x equals 1. Okay? At x equals 1, this function here is not defined. This function is defined for all x. So these two functions are actually equal at all points, except at x equals 1. So as you could see here, this is the graph of a rational function x cubed minus 1 over x minus 1. And this is the graph of the quadratic function x squared plus x plus 1. Notice that the two are the same, the two graphs are the same except at this point here. Where in here for rational function, this is undefined at x equals 1. So there's actually a hole at that point. Whereas here, this is a continuous function. This is a function continuous everywhere, so you still have a value here. So as you have seen here, these two functions are the same except at this point here. Now, as you might have noticed that when we simplify the function, our g of x, the function, the new function, which is a quadratic function, is a continuous function everywhere. And so therefore, if you take the limit of g of x as x approaches 1, you get a value. So the limit exists. Then you can now apply theorem 1.7 to conclude that f and g have the same limit at x equals 1. So for that, if we want to evaluate, so let's formalize this now. If you want to evaluate x cubed minus 1 over x minus 1, the first step is to see whether direct substitution can be applied. Now you could see directly that the denominator becomes 0. And so therefore, direct substitution does not apply. So what we would do is to factor the numerator, and that is just equal to x minus 1 times x squared plus x plus 1. And then just copy the denominator. And here, after this one, we can cancel the common factor, divide out the common factor. And so you're left with x squared plus x plus 1. And then take the limit of this expression here and then apply theorem 1.7. Evaluating the limit here would give us 1 squared, just direct substitution, and then plus 1 plus 1. This gives you 3. And so, therefore, the limit of this rational expression is just equal to 3. Also, I want you to bear in mind that when you're evaluating the limit, you are actually wanting to know where the function would approach to as the values of x would approach a certain point. So it doesn't really necessarily mean that the function is defined at that particular value of x. Now at this point, we can summarize what we have learned so far and come up with a strategy for finding limits. So the first step is to learn to recognize which limits can be evaluated by direct substitution. These theorems are actually, or these limits, type of limits are actually listed in theorems 1.1 through 1.6. Or if you're working on limits, the first thing that you should try really is the direct substitution. If it doesn't work, when would this one not work? It would not work if you get a 0 in the denominator. If you have a rational function and you get the 0 in the denominator, then direct substitution won't work. What else? If you have a radical expression, the one that involves radical sign, and then if the index is even, or if you have a square root function, and then you get the negative value inside the radical sign, then that would not also work. And so if first the direct substitution won't work, then we can use the theorem that we have just learned so far, wherein we will find an equivalent function by dividing out. Okay, so we can try to find a function that agrees with the given function for all x other than x equals c, or other than that particular point. And then when we come up, or when we can find that function, and that function, when you evaluate that function at x equals c, or when you evaluate the limit of that function using the direct substitution method and the limit exists, then you can apply theorem 1.7 to conclude that the limit of the function f of x as x approaches c is just equal to the limit of the new function g of x as x approaches c, and which is just equal to g of c. And third, you can also use graph or table to reinforce your conclusion. If direct substitution won't work in finding the limit, we can use the dividing out technique. This dividing out technique is a technique that involves dividing out common factors. For example, let us consider evaluating the limit of this expression here. Notice that if you're going to use direct substitution method, meaning you evaluate the limit of the numerator, which is x squared plus x minus 6, evaluate that at x equals -3, you get a 0. And then in the denominator, if I'm going to use direct substitution in evaluating the denominator, I'll also get 0. So from here we know that direct substitution fails. In this case, we can then use the dividing out technique. Now take note, when we evaluate the limit for both numerator and denominator, we both get 0 on those two. So that suggests that both numerator and denominator have a common factor. And the common factor is the factor that would make the denominator also 0. So that is actually the common factor that you would also have to look for in the numerator. So let's look at the example here. So for the numerator here, you expect to find this factor here because you know that this one is 0. So this is what is making the denominator equal to 0. Then you should expect to see that also in the numerator. And that is what we're actually trying to cancel out when we try to find the equivalent function. So you can check that the factor of x squared plus x minus 6 is equal to x plus 3 times x minus 2. Then you can cancel x plus 3 in both numerator and denominator. That means you divide out the common factor, and that is equal to, then you're just left with x minus 2. So this is just equal to x minus 2. And this is now our g of x. So we say that this g of x, x minus 2, is equivalent to f of x at x not equal to 3. So in other words, the g of x is just equal to x minus 2, wherein x cannot be equal to -3. Now using theorem 1.7, it follows that the limit of this function here is just equal to the limit of this equivalent function, which is just x minus 2, except that x cannot be equal to -3. And then you just take the limit of this expression here as x approaches -3. And therefore, the limit is just equal to -5, because using direct substitution, this is just -3 minus 2, and that is equal to -5. Now you can confirm your result by looking at the graph of the function f of x equal to x squared plus x minus 6 over x plus 3, and see that this is actually the graph of the function, which is about the same as x minus 2, except at x equals -3. Because here, the graph is just a line with a hole at x equals -3. Well, this graph here, or this expression here, has a graph of a line that is continuous everywhere. So these two are just equal or equivalent at all points except at x equals -3. And you can conclude you can verify your result by looking at the graph here. You see that the function approaches -5 as x approaches -3. So in the previous example, we have seen that if we use direct substitution, it would just produce a meaningless fraction of the form 0, 0. Now, if you find an expression such as 0, 0, that is called an indeterminate form. So it's called indeterminate form because from this form alone, you cannot evaluate or determine the limit. So when you try to evaluate the limit and encounter this form, remember that you must have to rewrite the fraction so that the new denominator does not have a 0 in it as its limit. And one way to do this is to divide out common factors. The next technique that you can also use is the rationalizing technique. Another way to find a limit analytically is by using the rationalizing technique, which involves rationalizing either the numerator or denominator of a fractional expression. Now, we know that rationalizing a numerator or denominator means multiplying the numerator and denominator by the conjugate of either the numerator or denominator. So for instance, let's rationalize the numerator of square root of x plus 4 over x. So when we rationalize the numerator of this, we will just multiply both numerator and denominator by the conjugate of the numerator, which is square root of x minus 4. So when you say conjugate, you just have to replace the sign between these two by the opposite sign. So from plus, the conjugate will be the minus. So the conjugate again of the square root of x plus 4 is the square root of x minus 4. So to rationalize this, we'll just multiply both numerator and denominator by square root of x minus 4. Now let's consider this example here. Now if we use a direct substitution method, you will obtain an indeterminate form of 0, 0. So if you try to evaluate the limit of the numerator as x approaches 0, you get 0. Similarly, if you try to evaluate the denominator as x approaches 0, you also get a 0. So therefore, you get 0, 0 here by using direct substitution. Therefore, the direct substitution method fails. In this case, we will use the rationalizing method to solve this since our numerator involves the radicals expression. So to do this, we will just multiply both numerator and denominator of this expression here by the conjugate of the numerator. So the conjugate of this expression is just copy the first term and the second term and then get the opposite sign of this, which is plus. So you multiply both numerator and denominator by the square root of x plus 1 and x plus 1 plus 1. Now, from here, then you multiply this to this using difference of two squares. You copy this expression here and then you square it, and then copy this expression here and square it. So to multiply these two, I just use difference of two squares formula. And then here, multiply this times this. Now, if you simplify the numerator here, removing the parentheses, you just get x in the numerator. And notice that that x can also be found in the denominator. So this is actually how we can factor out the x in the denominator, or we can cancel out x. So after we do the rationalizing method, then we also use the dividing out method. So we can cancel the common factor here, and then therefore we come up with an expression 1 over the square root of x plus 1 plus 1, and this is equivalent to this fraction here whenever x is not equal to 0. So these two will have the same graph except that x equals 0. So now using theorem 1.7, we can now evaluate the limit of the square root of x plus 1 minus 1 all over x by just evaluating the limit of the equivalent rational expression, which is 1 over the square root of x plus 1 plus 1. Using direct substitution, we can evaluate this limit. We will replace x here by 0. Therefore, we have 1 over 1 plus 1. That is just equal to 1/2. Now, our result can be reinforced by just looking at the graph of this function here. If you notice, if you look at the graph of this function, you'll see that close to x equals 0, near x equals 0, the function is going or approaching to y equals 2. So the limit of this function as x approaches 0 is 1/2. And also, if you want to just use a table to confirm your result, you can look at values at the left side of 0. So small values very close to 0 from the left. These are the negative numbers really close to 0 from the left. And the values also to the right of 0 or coming from the right of 0. These are these numbers here. And then just use these numbers to plug into our function f of x and evaluate the function at these points here. You would notice that as x goes close to 0, the value for your f of x also approaches 0.5. So that is the same also for the values of 0 coming from the right of 0. As you approach 0 from the values to the right of 0, coming from the right of 0, as you move closer and closer to 0, the y values also goes closer and closer and closer to 0.5. Lastly, let's discuss the squeeze theorem and how we can use this to evaluate limits. This next theorem here concerns the limit of a function that is squeezed between two other functions. Let's say, for instance, this function f here, this is squeezed between g and h. So as you see in the figure here, each of the three functions here has the same limit at the given x value. As x approaches c, all these three functions here have the same limit. And f here is a function between h and g. Now let's discuss theorem 1.8, also known as the squeeze theorem. Here, suppose you're given three functions, f of x, h of x, and g of x, such that f of x is greater than or equal to h of x, and also at the same time less than or equal to g of x, for all x in an open interval containing c, except possibly at c itself. Now, if the limit of this function as x approaches c is equal to L, and also the limit of this function g of x as x approaches c is also equal to L, then the limit of the middle function f of x as x approaches c exists and is also equal to L. This squeeze theorem is also known as the sandwich theorem or the pinching theorem. Now, there are also two special trigonometric limits that you need to just memorize at this point. This is the limit of sine x over x as x approaches 0, that is equal to 1. And whenever you see the limit of 1 minus cosine x over x as x approaches 0, this is equal to 0. The derivation of this, or you would learn how to solve this later on, but at this point, just accept this to be true. If you do substitution method, you get an indeterminate form, a 0 over 0, both in these two numbers. And later on, towards the end, we have a separate discussion on how we would evaluate limits for expressions that are indeterminate, or we will discuss all other indeterminate forms. Let's take a look at this example here and see how we could use those known limits to solve the limit of this trigonometric function. So let us evaluate the limit of tangent x over x as x approaches 0. First, if you use direct substitution, this will yield to an indeterminate form of 0 over 0 because tangent of 0 is 0 and x replaced by 0 is just 0. Then what you will do then next is to just rewrite tangent. You know, tangent is just equal to sine over cosine. So we will rewrite tangent x as sine over cosine and write it this way. So this may be rewritten as sine x over x times 1 over cosine x. You can verify by just multiplying these two and you would get back to the original form. Now also, we know that the limit of the product is equal to the product of the limit. So all we need to do is evaluate the limit of this expression and then multiply that result to the limit of this expression as x approaches 0. Now, from the previous theorem, we've seen that the limit of sine x over x as x approaches 0 is just equal to 1. So we'll just accept this to be true. And then we can evaluate the limit of this expression. The limit of 1 over cosine x is just equal to 1 because cosine of 0 is also equal to 1. So you have 1 over 1 is equal to 1. Then you plug this in here. As I've said, the limit of the product is equal to the product of the limits. So the limit of tangent of x over x as x approaches 0 is just equal to the limit of this expression, which is equal to 1, times the limit of this expression as x approaches 0, which is also equal to 1. So therefore, we have 1 times 1, which is equal to 1. So the limit of tangent x over x is equal to 1. We can verify our result by looking at the graph of tangent x over x. And by looking at the graph of tangent x over x, if we take the limit as x approaches 0, if we look at the values of y as x approaches 0 either from the right or from the left, we know that the function approaches this point here, and that is at y equals 1.